All right, so we're looking at solving polynomials over the complex numbers. So basically just this idea that if you get given some polynomial, you can obviously find any real solutions given all the stuff that we've learned about polynomials in the past, but you can also solve it over the complex numbers. So see if there's any complex number solutions to the polynomial. What I would just say is up to this point, we've done a lot on complex numbers. I'd strongly recommend that you go and watch all these other videos. I'll put the links below for these. And then what we'll talk about in this video is obviously polynomials over the complex numbers. So we'll look at the factor and remainder theorem, look at what's called the conjugate root theorem, and then we'll do a visualization of the root theorem. And then we're going to look at what's called the fundamental theorem of algebra. So it's getting quite tricky, but interesting nonetheless. So let's jump into it. So when we're talking about polynomials over the complex numbers, what we have is just our general polynomial, so p of z. We've got these coefficients a(n), a sub n minus 1, all the way to a naught, and they can be complex coefficients, which is what makes this sort of a complex polynomial. And obviously the first term isn't zero. So we can also say a lot of similar things to just dealing with complex numbers in real number land. So if you were to divide some polynomial p of z by some other polynomial d of z, then you would get this situation, right? We get p of z divided by d of z, p of z divided by d of z, giving you q of z, and then some remainder. So this is the quotient, and then the remainder. Okay, just by that logic, I think you would agree that the degree, so the size, the highest power of d will be greater than the remainder, right? And that's a lot of sort of polynomial long division stuff that you might need to sort of remind yourself of a little bit there. But basically, you know, for example, if this was a cubic, d of z might be linear, and then therefore q of z has to be quadratic. And then if there's any remainder left over, it's going to be less than the size of d of z. Okay, and we know that if r of z equals 0, then d of z is a factor of p of z. So yeah, if there is no remainder, then d of z went into p of z nicely. And so it's completely analogous to the remainder theorem and the factor theorem in normal number land. So the remainder theorem says that if alpha is an element of the complex numbers, the remainder of p of z divided by z minus alpha is p of alpha. Essentially just this idea that if you sub in alpha, or you sub in that number, then that's going to give you the remainder. Yeah, the remainder is equal to p of alpha. And similarly, the factor theorem says that if z minus alpha is a factor of p of z, then this implies that p of alpha equals 0. Okay, so that's a situation where this part doesn't exist. R of z is equal to 0. So maybe an example will help here. So we're going to look at the factor theorem. So we've got some polynomial, p of z, and we get this z cubed plus 3z squared plus 7z plus 5. So p of negative 1 turns out to be 0. If you substitute negative 1 for z here, you'll get 0. Therefore, z plus 1 is a factor. Okay, because remember, if you're dividing by z minus alpha, then p of alpha is a factor. So you take the opposite sign of this. So what that means is z plus 1 is a factor. Okay. Then just sort of by inspection, or you can do the long division if you like, or the re-expression, you'll be left with this quadratic z squared plus 2z plus 5. So just to be really clear, if we multiply these two things together, we'll get back here. Okay, and then what we can do, a little tip here is obviously leave the z plus 1, but then we take this and then we complete the square. So we get z squared plus 2z plus 1 minus 1 plus 4. And basically just completing the square on that, and then you'll be able to express it like this. And then from there, you can use a difference of perfect squares. So you get z plus 1 multiplied by z plus 1 minus 2i multiplied by z plus 1 plus 2i. So p of z equals 0 implies that z equals negative 1. It also equals negative 1 plus 2i and negative 1 minus 2i, just by applying the null factor law to this. So that's how we sort of... there's a nice example of applying the factor theorem to a polynomial over the complex numbers. So we've got three solutions there. Okay, hopefully that makes a bit of sense. I think this image summarizes the whole thing for you as well. Okay. Next thing we're going to look at is what's called the conjugate root theorem, which can be quite tricky, but it's interesting when I sort of show you a picture of it. So consider the polynomial. Again, we've got some polynomial just like we had before. Okay, where all a sub r are real. So all the coefficients are real coefficients. And we're going to say that some complex number alpha is a root of p. So what we're saying is that p of alpha equals 0, just like we saw before. Whatever this number is, this complex number is, it's equal to 0. And we want to show that p of the conjugate of alpha equals 0 as well. So you can see why it's called the conjugate root theorem. So we want to show that that's true. All right, so what we start is with this. So if p of alpha equals 0, then we know that this polynomial is equal to 0 when we substitute in alpha for z, right? So what we've taken this, we've set it equal to 0 and replaced z with alpha. Okay, and so what we can do is we can actually use a bit of this notation here, and what we say is we can write it as the sum of all of these terms from r equals 0 to r equals n of a sub r multiplied by alpha to the r equaling 0. So that's just basically rewriting this, but using some notation. And then what we say to ourselves is, all right, well, let's consider what happens if we take p of the conjugate of alpha. So then we're basically taking this alpha term and making it the conjugate. And then we can use the properties of complex conjugation. Now, this is it all written out in some notation, but I think it's actually probably easier if we use this, use this up here. So just a reminder of some of the properties of complex conjugation over here. Just have a look over these. If you take the conjugate of a sum, it's the sum of the conjugates. The conjugate of a product is equal to the product of the conjugates. And also this one down here is relevant. If you take a conjugate of a power, it's equal to the conjugate raised to the power. Anyway, if we take this line here, and then we say, all right, alpha is now the conjugate, so we replace it with the conjugate. And then we say by this rule here that that's the same thing as taking the conjugate of the whole thing. Okay, and then we can say, all right, this is equivalent to taking, when you multiply by a scalar, which is not there, when you multiply by a scalar, alpha naught, when you a naught multiplied by alpha naught, so basically this term here, a naught multiplied by the conjugate of alpha to the power of 0 is just the conjugate of alpha naught, alpha to the power of 0 multiplied by a naught. That's another property of complex conjugation that's actually not there. In any case, you do that for each term, and then we know by this first rule that that's the same thing as the conjugate of the whole thing. Okay, so after all of that, we can say that basically you take the conjugate of all of this, which is this line here. So that's the same thing as taking the conjugate of the right-hand side, which is the conjugate of 0, because we know that this whole thing is equal to 0. And so we can see that p of alpha, the conjugate of alpha, is equal to 0 as well. Okay, and which is just this line here. All right. Eddie Wu makes an interesting video about this. It explains it better than I do, so I'll put that link below as well. So this works only because the coefficients of alpha sub r are real, and so the conjugate of alpha sub r equals, I can't even read it. This works only because the coefficients of a sub r are real, so a sub r, the conjugate of that is equal to a sub r. If the coefficients were not real, the roots would not necessarily come in conjugate pairs. Okay, so in fact, for any alpha that's a complex number, we have p of the conjugate of alpha is equal to the conjugate of p of alpha, even if p of alpha is not equal to 0. Okay, the key takeaway from this is that solutions to polynomials come in conjugate pairs. And what we're going to do now is we're going to actually visualize that. So if we have a look over here, visualizing the conjugate root theorem. So we've got our polynomial, looks like this. And what we have here is I've got all these sliders where I could just change the coefficients of all these terms. I've just gone up to a power of 5 for our polynomial, but we can see that I can just change these coefficients. And what we have here in purple is what's called the modulus surface. So let me explain what that is. The modulus surface is basically this idea that the x value represents the real component of the complex number. Now remember, z is a complex number made up of a real part and an imaginary part. So x plus I, y. So the x part is the real part of the complex number. The y coordinate on this Cartesian coordinate system is the imaginary part of the complex number. And now what we're going to say is the z coordinate is equal to the modulus, so which is just this, right? Is the square root of the real part squared plus the imaginary part squared. That's what the z coordinate is equal to. And so you can see that we have all these points where this surface seems to go to 0. We've got 3 points in this case where the surface seems to go to 0. And I really just want to drill down in that so you're super clear. The real part squared. So remember, these polynomials that we've got, so let's just look at this one here, are made up of lots of expansions of x plus iy. So x plus iy times x plus iy times x plus iy would give us z cubed. Expand all that out, collect the real components, and then collect any like terms with all the other ones when you do the same thing, and you will get the real component, and then you square that real component. Okay, and then that's the real component squared, and then you sort of graph the surface, which is what we're doing here. In any case, you'll see that this here, these terms are 0, but this part here is the surface, is the polynomial that we had from before. So if we go back here, z cubed plus 3z squared plus 7z plus 5, you can see that that's what we have here, right? So what you'll notice is where this goes to 0 is actually the solutions. So if we just quickly check what were our solutions. Well, I had one at -1 plus 2i, and -1 minus 2i. So if we come over here, we can see that the x-axis, this point here, is at -1, which is one of our solutions. Okay? And then you can see that the other ones come in conjugate pairs. This one is a reflection across the real axis of this one. So what I mean by that is, you can see this point here must be at -1 plus 2i. Remember, the y-axis represents the imaginary component. So this point here where it goes to 0 is -1 plus 2i. This one here is -1 minus 2i. And so you can see this one and this one come in a pair. And you'll notice if I start changing these terms, just for illustration purposes, you can see that they always come in conjugate pairs. There's always a pair of solutions, which is what we're talking about, the conjugate root theorem. Okay, so this polynomial, z cubed plus 3z plus 3, is another example you can see where we get conjugate pair solutions. Okay, so tricky idea, but hopefully it's making some sense. Let's have a look at another example. Here's another example that I had prepared before, but then I realized it doesn't have any complex solutions. So I'll just leave this here for you to look at. So pause the video and have a read. Basically, we've got this polynomial, and basically when we factorize it, just using the rational root theorem, because this has all rational roots, we get solutions at 2, 3, and -2. And so what I'm going to do is I'm just going to set the coefficients equal to these. So I just got to remember this: 1, -3, -4, 12. So 1, -3, -4, and then this one's 12, I think. All right, and sure enough, our modulus surface now has solutions where we said they would. One at 3, one at 2, and one at -2, which matches our solution to this example that you can work through. So you can see that this modulus surface is a nice way to visualize the conjugate root theorem as well. I should just point out that when the answers are real, the conjugate pairs are themselves. So the conjugate root theorem still holds up. It's just that they're on the real axis. So you can't reflect. Remember, a conjugate pair reflects across the real axis. So when all the solutions are real, you're not getting the sort of reflection across the real axis because they are on the real axis. But you can see otherwise, if we just change it a little bit, you get conjugate pairs. Okay. All right, so just the last thing in this video, we'll talk about what's called the fundamental theorem of algebra, which sort of ties this all together, hopefully a little bit. So what we say is for any polynomial with complex coefficients, where n is greater than or equal to 1, obviously, we're saying that the power of this isn't 0. What this very intelligent man, Gauss, found out is that it has at least one root in C. So there's at least one solution in the complex plane, was sort of his first conclusion, okay? And then, what he said from there is if you repeatedly apply the fundamental theorem of algebra, so basically if you have some polynomial and then you find one of those solutions, you've basically found something like this. You found z minus alpha sub 1, okay? And then you're going to be left with some q of z from before. You're going to be left with some other polynomial term. But then if you apply the fundamental theorem of algebra to that, you're then going to get a situation where you keep finding solutions to your polynomial in the complex plane. So you're going to end up with this. You're basically going to get your polynomial is going to be able to be expressed as a sub n, z minus alpha 1, where alpha 1 is a solution, z minus alpha 2 is a solution, all the way up to z minus alpha sub n. And so you can see that if p of z equals 0, then the solutions are alpha sub 1, alpha sub 2, all the way up to alpha sub n. These are known as roots or zeros of p of z. Okay, so what the next step he was able to say is, okay, so a polynomial of degree n has exactly n complex roots, counting repeated roots. Okay, so yeah, if this is a 3, then you're going to have 3 complex roots. But you need to account for the fact that you could have repeated roots. So if you had z minus alpha cubed as your p of z sort of factorized, then that would count as 3 solutions because you have to count the repeated roots. Anyway, hopefully that's making some sense. It's hard. It can be a challenging concept, but hopefully you're sort of wrapping your head around it. I was just looking at if you're interested. Gauss is an interesting guy, sort of French Revolution times. He came up with this when he was like 22 years old in his sort of doctoral papers. So pretty impressive stuff to think about this. But by all accounts, a pretty meticulous sort of man. Very conservative apparently in his views about the revolution and things. So, I don't know, it's just nice to remind us sometimes that, real people are coming up with these ideas and, we sort of carry the torch with some of these things that we're learning about as well. So as always, if you find this video useful and you sort of made any sense of it, give us a thumbs up. If you need any private tutoring or just need a hand with any of the maths that you're doing, let me know and I'll be happy to have a chat. Good luck with everything you're doing. I'll talk to you soon.